Hi, Dr. Pat here. We're looking at logarithmic functions. Going to have a little fun with this one. There's actually some research on happiness, and we'll be looking at that and seeing that a logarithmic function can actually model that. And so happiness with dollars. So how satisfied you are with your life versus the dollar amount. And so it follows a pattern here. And this would be the characteristic of a logarithmic function. So let's take a look here. So what we have here is some people doing some research, and they were looking at how much the gross domestic product per capita, that's basically an average per person for a country, what they produce and sell kind of stuff. And so we're seeing a lot of countries here, below 10, I think that's $10,000 per person in their country. And so what we've got here is a model here that this is a fitting line here. So what we're looking at is as we increase the gross domestic product per capita, as each person kind of gains money, we're not seeing a dramatic increase in the satisfaction for life. So at the happiness. And so what we're seeing is in the early stages, yes, you increase money, people are going to have a large increase in happiness. But after a while, happiness, money isn't going to buy you too much more happiness. It's going to take a lot more money to get the same amount of happiness change. And so that's basically a logarithmic function. That little nice characteristic there, steep in the beginning, and then kind of appears to level off a little bit. So steep over here to the left in the beginning, and then kind of levels off that appearance that way. And so that's logarithmic. It's kind of like an exponential, but just kind of flipped. And so another example that we have for a logarithmic model is basically box office receipts. Most of your movies follow this generic pattern of steep in the beginning and then level off. So a lot of people seeing movies at the beginning when the first 2 weeks that a movie's out, a lot of people are seeing it. That's why you see steep at the beginning, but then the box office receipt starts to level off. And so just having fun with Hansel and Gretel, the witch hunters. A nice little formula up there. Hey, that's how they got their powers. And so here's our model for logarithmic. It's ln, that's the natural log, if you heard that before. And so this is what you'll see in your calculators or the technology. And so a, they're kind of a steepness indicator. So the larger value for a, the steeper this thing gets. The smaller the value for a, you get more of a shallow kind of graph. So just kind of let you know that. Also, the c value here is the value at time 1. Because on the normal, just plain old logarithm, you have a value of 0 when it crosses there. So when you add this c value, you're basically shifting up the natural log graph. You're just shifting that up. And so that's kind of an indicator for us at time 1. Because you plug 1 into a natural log, and you get 0 as the result there. All right, so that's basically our formula we have for logarithmic. So if you were to put this data points I have for the Hansel and Gretel, I got this off of a website. And so here's the box office receipts, 3 days since opening, 10 days since opening, and then we basically have the running total for our box office receipts for this movie. So this last one here, 33 days in the movie theaters, and we have a total of $53.3 million. Okay. Excuse me. And so what we're looking at is input those data into your stat feature of your calculator, the TI-84. Then after you've inputted it, the days in L1 and the box office receipts in $1 million in L2, go ahead and go to Stat Calc, and then you want to highlight, access the linear regression model. And so if you do access that and hit enter and then press enter again, what you'll get is a nice formula. I rounded off to 1 decimal place. And here's our formula that we could use that models the box office receipts for Hansel and Gretel. And so that's an example of natural logs. So now one of the questions we could have with this movie, if production costs for the movie were $50 million, when does the movie, typo there, movie break even? And so that's what we're looking. So we're looking for when the graph crosses 50 million. So here's our graph. We're looking at 50 million there. We want basically this idea here. And so from that graph, I'm kind of thinking either 25 or 26. So somewhere around there. So somewhere around 25 or 26 days in the movie theaters is when we break even. So it took a while for this movie to break even. And so after that point, this is how much profit they're making then. Okay, because we've got our cost and then our revenue. Revenue eventually gets higher than the cost, so we've got profit. And so now how would we find it algebraically? So what we have is 50 equals 3.2 plus the 14.4 LNT. There's our model. And so we set that equal. And what we've got to do is we got to get t by itself. So what we have to cancel is the 3.2. Got to get rid of that 3.2. Got to get rid of this 14.4. And then we have to get rid of the natural log. So we have three things. We have three steps in order to solve for t. All right, and then just remember one of the things that we're going to play with is that ln and e, the exponential base e, they're opposites of each other. Okay, so just keep that in mind that the natural log and the exponentials, they're inverses, opposites. All right, so let's kind of look at our steps here. Started with the function, and what I'm going to do is first subtract 3.2. So to get rid of the 3.2, it's adding. So to cancel it, you subtract it. And this is where that 46.8 is coming from. Then for the second step, we want to get rid of the 14.4, so we'll divide that 14.4 because it's multiplying, and the opposite of multiplying is dividing. Yeah, I know I'm being kind of slow here, kind of redundant, it's really saying it out, but I really want to get the idea here is that when we're solving for an equation and we're solving for t, we're always doing this canceling, we're doing the opposite thing. So if we're adding, we subtract. If we're multiplying, we divide, always doing the opposites. So now when we get to this point right here, where we want to get the t by itself, we want to get rid of the ln, that's natural log, that's log base e, what you have to do is the opposite, and the opposite of logarithms is exponentials. So then what we're going to do is do the exponential base e. And what I mean by that is take both sides individually and put it into the power with a base e. So these are exponentials. So the e is technically a number. It's like pi. Pi is 314 blah 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 blah. E is a number as well. It's 2.71 blah blah blah. And so that's what we're playing with. The key thing here is why do the e is because the e and the ln will cancel each other out, leaving us the t. So we're going to end up with t equals the exponential base e to the power and this fraction. So if you're going to type this into your calculator, look for the E key, and that basically should be the second feature of the ln button. And then make sure you put that in parentheses, this fraction here, this 46.8 divided by 14.4. Make sure that goes inside parentheses, and when you do that, you get an answer of approximately 25.8. So there we go. From the graph, we had something like 25.26, and then from the algebra, we get 25.8. I'm thinking that confirms, and I'm good to go. So have a good day. Talk to you later.